This video is for section 7-5, properties of radicals. Let's begin with this theorem, the product property of radicals theorem. If n is a positive integer and all of these expressions are real numbers, then this is true. The nth root of a product is equal to the product of nth roots. You can kind of think of this as factoring, rewriting this product as the two factors that multiply together to create it. With that theorem, we can simplify expressions involving radicals. Let's say we wanted to find the square root of 242y cubed. We can rewrite that as a product of square roots. For example, 242 is equal to 121 times 2. And y to the third power is equal to y squared times y. Now you might be wondering, why would you write it like that? The reason is that in the first radical are perfect squares. The square root of 121 makes 11, and the square root of y squared makes y. The other radical does not have perfect squares inside of it, and so you would leave that piece in a radical symbol. The square root of 242y cubed can be rewritten as 11y times the square root of 2y. Let's try another one that involves a cube root. To find the cube root of this expression, we can rewrite it as a product of cube roots. Now let's think about what factors to write in the first radical and what factors to write in the second radical. In the first radical, we want to have only perfect cube numbers so that when you find the cube root, you get whole numbers. 64 is a perfect cube already, so let's leave 64 in there. X to the first power, however, is not a perfect cube. Let's put the x factor in that radical. Y to the sixth power is a perfect cube, so we'll leave it in the first radical. One more step. Find the cube root of every factor written in the first radical. The cube root of 64 is 4, and the cube root of y to the sixth power is y squared. Leave the other radical in radical notation. Here's another theorem. If m and n are positive integers and b and the nth root of b are real numbers, then this statement is true. Finding a root of a power is equivalent to finding the power of the root. Let's try some examples of that. To find the fourth root of 16 to the third power, we could rewrite this as the fourth root of 16 raised to the third power. The fourth root of 16 is 2, and 2 raised to the third power makes 8. Next example, to find the cube root of a number to the second power, we could find the cube root of the number and then raise that to the second power. The cube root of negative 27 is negative 3. And then when you raise that to the second power, you get the answer 9. Another theorem, the quotient property of radicals. If n is a positive integer and all of these expressions are real numbers, then this statement is true. The root of a quotient is equal to the quotient of roots. This is related to the product property, where you could separate a product into two pieces. Here we're separating the quotient into two pieces. Here are some examples of that. Let's say we wanted to find the square root of the quotient y to the 8th divided by 32,400. We could rewrite this as the square root of y to the 8th power divided by the square root of the 32,400. The square root of y to the 8th power is y to the 4th power. And with the help of a calculator, the square root of the denominator is 180. Next example. This one uses the converse of the theorem. Instead of having a square root in the numerator and another square root in the denominator, we could rewrite this using a single square root symbol and form a quotient from the radicands. Then simplify that fraction that's in the square root. 98 divided by 2 is 49, and t to the third power divided by a single t is t to the second power. These are both perfect squares in the square root, so the final answer is 7t. The theorems enable us to simplify terms involving radicals with index n. Terms with radicals are in simplest form when the following criteria are met. So you know in algebra, we're always trying to put our answers in simplest form, but sometimes it's unclear what that means. How do you know how far to take an answer so that you get it to what mathematicians call simplest form? In the case of radicals, these are the 4 rules to follow. No radicand that's an integer can have a factor that is the nth power of any integer other than 1. That sentence is a little confusing, but we applied it in the last example that we did. I knew that this was not simplified because 49 is the same thing as the integer 7 to the second power. And that power matches the index of a square root, which is always a 2. Second criterion, no polynomial radicand can have a factor that is the nth power of any polynomial other than 1. That rule came into play with the variable piece. I knew that this wasn't simplified yet because the variable's power of 2 matches the index of 2. You can actually find the square root of t to the second power. It makes t. The third criterion is that there can be no fractions or powers with negative exponents under the radical sign. That was the rule that we applied for this example. There's a fraction under the radical sign, so this was not simplified. The fourth rule is that no radical can be in the denominator. And that rule applied to that very last example. Because there is a radical in the denominator of this expression, it was not simplified. If you're expected to simplify an expression that has a radical, these are the 4 rules to run through to determine if you have simplified the expression. Make sure that there are no radicals in a denominator. Make sure that there are no fractions under a radical. Make sure that no variable terms have a power that you could take the root of that power. And make sure that no numbers in the radicand can be factored in a way that you could take the root of one of those factors. One of the rules is that there can be no radical in the denominator. To accommodate that last criterion, you can use a process called rationalizing the denominator. For example, let's say we want to simplify 6 divided by the square root of 2. This has a radical in the denominator, which means it's not simplified. How do we correct that? Rationalizing the denominator is the process of multiplying the top and bottom of the fraction by the denominator. Because you're multiplying top and bottom by the same thing, you're not changing the overall value of the fraction. Then write down what this creates. In the top, we have 6 times the square root of 2. In the bottom, the square root of 2 times the square root of 2 is equivalent to the square root of 4. But that just makes 2. Then we can simplify the whole numbers 6 over 2. Final answer is 3 square root of 2. Next example. We have the cube root of this expression. This is not simplified because it has a fraction, but also because it has a negative exponent in the radical. First step, let's rewrite that and correct the negative exponent. This is equivalent to 1 over 200 r to the 4th power. Next step, let's apply the quotient property and rewrite this as the cube root of 1 divided by the cube root of 200 r to the 4th. The cube root of 1 is just equal to 1. So we can rewrite this as 1 over the cube root of 200r to the fourth. But we're not done because there is a radical in the denominator of a fraction. So let's rationalize the denominator. Multiply the top and bottom by that radical. This will equal 3 cube root of 200r to the fourth power over 200r to the fourth power. Is it done now? Let's run through the rules. We no longer have a fraction under a radical. We no longer have a radical in the denominator. The number 200 is not a perfect cube, but it can be factored where one factor is a perfect cube. So we need to rewrite this as a cube root times a cube root. Remember that this is over the denominator of 200r to the fourth power. Now what perfect cube is a factor of 200? That number is 8. 8 times 25 is 200. Now let's look at the variable term, r to the fourth power. Because this power is greater than or equal to the root, we can factor it as r to the third power times r. Now we can get to the final answer. The cube root of 8 is 2. The cube root of r to the third power is r. The other radical stays as a radical. And this is all divided by 200r to the fourth power. Final step is to reduce. The 2 over 200 reduces to 1 over 100. The r in the top will cancel away one of the r's in the denominator, leaving r to the third power. And the radical stays in the top. So this expression took several steps of work in order to follow all 4 of the rules for simplifying a radical. But the more practice you have with these, the faster they'll become, because you'll notice where you can combine steps. Let's summarize the lesson. We discussed some theorems that are used to simplify radicals. There are a couple reasons why you want to simplify radicals. One reason is working with a radical might be only one step of a larger math problem. A second reason is so that your answers look like the answers that other mathematicians get. In a school math class, the answers are often given, for example, in the back of the book. And for you to check your own work, you need to know if your answer is equivalent to what is in the back of the book.